Alright, so in this video we'll be looking at a more formal mathematical definition of continuity. So in the last video we kind of defined continuity or function being continuous if you're able to draw its graph without picking up your pencil, right? And so clearly that's not a very mathematical definition. So in this video we'll just be looking at the three conditions that must be met by a function in order for us to formally kind of say that it is continuous at a specific point. And so again, this is at a specific point. So if we have, let's say, some function f of x, in order for us to say that f of x is, that's a weird I, is continuous at, when x is equal to some point a. In order for us to be able to say that f of x is continuous at some point a, right, we need to actually meet these three criteria. The first one makes a lot of sense, right? The first one is this value, f of a, actually has to be defined. So f of a is defined. What that means is, again, if we plug in this value a to our function, we get some real answer, or a is within the domain of this function, rather, right? Is another way of saying this. So obviously, if we are not getting a real answer here, then we can, pretty easily say that this is not a continuous function. The second criteria here that needs to be met is that the limit as x approaches this value a for f of x must exist. So this limit must exist. And what that means from more of a graphical perspective is if we have a function, for example, this is our function here, and this is the point, our point A, we need to see that when approaching A, if this is our A, from both the left and from the right, we are approaching the same value, right? We are familiar with, limits at this point. We know the left-handed limit and the right-handed limit must agree in order for the limit to exist. So that's what we're checking here. So again, this limit must exist. And that also makes sense, right, for a function to be continuous. That means it makes sense that we must have the same point that we're approaching from both directions. And the last criteria here, the third and final criteria, is that this limit that we were just talking about, this limit as x approaches a for f of x, it actually must equal our f of a. And this kind of makes sense if we're looking at things like holes, or when we were speaking about, limits in one of the very first videos of this series, we talked about, for example, that a limit can exist, but it doesn't necessarily mean that the f or the value of the function at that point is the same. For example, if we had a function like this where we have a hole at this point and then a dot or point above here, we can say the limit does exist. We are approaching the same point when we're trying to find the limit here. But this is not the point where the function actually has a value, since we have a hole. So if we actually plugged in this a into our function, we would not get any real number, as this is our actual point. So and then this is clearly not continuous, right? This is a hole, something we talked about in the last video. So clearly, in order for the function to be continuous, that means that this point f of a must equal the limit. So hopefully this is making some sense. So these are the three criteria or parameters or conditions that need to be met in order for us to formally say that our function f of x is continuous at this specific point. So now let's look at some examples just to make this a bit more clear. So we can start with an example of a polynomial function. And this is something, again, a polynomial is one that we know to be continuous, but this is just more to reinforce the points and see if, these criteria actually do hold. So let's say we're looking at this function here. So we're trying to see if the simple polynomial x squared plus 3x plus 2 is continuous at this point when x equals 1. So, obviously, we know polynomials are continuous everywhere, but this is just to check with the three conditions. So if you remember, the first condition here that we're trying to find out, right, or that we're trying to confirm, is that our f of a actually is defined. So here our a is 1. So if f of 1 exists, we can see 1 squared plus 3 times 1 plus 2 plus 2. This is going to give us 6, and 6 is obviously within the domain of this function. It is clearly a defined value. Okay, so the first criteria is met. Now what about the second one? For the second one, we need to find the limit the limit as x approaches 1 of our function f of x. So again, this is a polynomial, so we can use direct substitution here. So using direct substitution will actually just give us the same answer that we got here, but just for, working it out to show our work, we can show we're using direct substitution, and we will get 6 here. And so the limit exists. And now what about the third and final criteria? I mean, after doing this, we can see pretty clearly, but, just for clarity purposes, we need to see if the limit as x approaches 1 of f of x is equal to f of x. So is equal to f of 1, rather. So here we can see that our limit is equal to 6, which is also equal to our f of 1. So all three criteria here are met, and so we can say that f is continuous at x equals 1. All right. So hopefully this is making some sense. This is the type of work that you would need to be showing on an exam in order to gain credit. All right, let's look at this rational function now. So this is a type of function that we've seen has a hole in the last video, but in any case, let's try to confirm that with these criteria. So the first thing we want to check, obviously, is to see if our f of, in this case, 1 exists. We're trying to, again, see if this function is continuous at x equals 1. So does f of 1 here exist? Well, plugging in 1 into this function gives us 0 over 0. So this is undefined. So we actually have failed the very first criteria itself, which means we can just say that it's non-continuous. But let's just continue on to see. Let's just continue with the rest of our tests here. So what about the second one? Does the limit as x approaches 1 for our function f of x exist? Well, clearly we can't use direct substitution. So let's see if we can use any of the other tricks that we've picked up over the past few videos here to figure out this limit. Well, let's try it. We can try to use factoring and canceling to see what happens here. So we can clearly factor the top one, the numerator here. That's difference of squares. So we can see that gives us x plus 1 times x minus 1 divided by x minus 1. So that allows us to cancel out the x minus 1 and x minus 1, leaving us with the limit as x approaches 1 of x plus 1. Using direct substitution, we can see that gives us 2. So the limit does exist. The limit exists here. And now, clearly, the third criteria is not met. Since f of 1 is not defined, condition 1 fails, and so we can't even see if f of 1 is equal to the limit here. And so here, the limit does exist, so this, I guess we failed this too. So what we would say then is that the limit exists, but the function's value doesn't. And so from this, we can again see that this is a removable discontinuity. This is a hole at x equals 1. All right, now let's just look at another example here. Let's look at a piecewise function. That's another common place where we can try to see jump discontinuity, something that we actually didn't get a chance to look at in the last video. So let's see if we can find a problem like that. All right, so let's look at this piecewise function here. So we're given a function f of x, where the function is x squared for all values of x less than 2, and it is 3x minus 4 when x is greater than or equal to 2. So we need to see if we need to figure out if this function is continuous at x equals 2. So let's just jump right into this, just as we would with any other of these continuity problems. We're first going to see if the first criteria is met, right? Does our f of 2 exist? Is this a defined value? So which branch of the function do we use here, though, however? Where do we plug in this 2 into our function? Well, clearly, if we're trying to find f of 2, we're going to use the branch where this is actually defined, right? Here, x squared is when x is less than 2. So we're going to use the 3x minus 4, because that is when x is greater than or equal to 2. So we would simply plug in this value of 2 into our function, or this branch of the function, that is going to be 6 minus 4 or 2. And this is clearly a defined value, and it's within the domain of this function. So the first criteria is met. Now for the second one, we need to find the limit as x approaches 2. But again, since we're dealing with a piecewise function, this is something that we've seen before, we're going to need to see if the left-handed limit and the right-handed limits agree. So let's first find the left-handed limit. Let's call this the left-handed limit here. So that would be the limit as x approaches 2 from the left for our function f of x. And again, in this case, that will be for x squared. The left-handed limit would be for x squared. So we can simply use direct substitution here. And that is going to give us an answer of 4. So the left-handed limit exists. Okay, so far so good. Now looking at the right-handed limit, let's see what that is. That is the limit as x approaches 2 from the right. And so we would be using our 3x minus 4 for this part. And again, we can simply use direct substitution, but that is going to give us a value of, again, 2 times 3 is 6, 6 minus 4 is 2. So unfortunately here, we can see that our left-handed limit and our right-handed limit do not agree. These are not the same value. So these are not the same value. What that means then, again, if we wanted to write this formally, we would say, again, the limit as x approaches 2 from the left for our function f of x does not equal the limit as x approaches 2 from the right. And so because of this, the limit does not exist. The double-handed or the double-sided limit, right? Because the two sides do not agree, the limit does not exist. And so then as far as for the third parameter, again, since the condition 2 itself has failed, we can say that the function is not continuous. So if any one of the three conditions are not met, the function is not continuous. And so here we can simply say, right, because the left-handed limit and the right-handed limit disagree, there is going to be a jump discontinuity at x equals 2. So the function is not continuous, and in fact, it actually has a jump discontinuity at x equals 2. So that is how we solve this problem. So let's see. All right, now let's look at this problem here. So we're given another piecewise function, but here, as opposed to the previous problems, we need to actually figure out what value of k for this function would allow it to be continuous at x equals 1. So we're given this piecewise function where 3 minus x squared, or the function is 3 minus x squared when x is less than or equal to 1, and it's 5x plus k when x is greater than 1. So we now need to figure out for what value of k can this function be continuous at x equals 1. So there's no need to approach this in any way other than what we've already been doing. So let's just first look at the first criteria, if the first criteria is met. So in this case, we need to see if f of 1 is defined. So f of 1, we're going to have to use this upper branch here, clearly. So we're simply going to substitute 1 into this expression, and that gives us 3 minus 1, or 2. And this is clearly a defined value. Now, we need to now find the limit as x approaches 1. And again, since we're dealing with a piecewise function, we're going to approach this the same way we did for the last problem, where we need to compare the left-handed limit with the right-handed limit. So starting off with a left-handed limit, what is the limit as x approaches 1 from the left for our function f of x? Again, for the left-handed limit, we would be using this 3 minus x squared branch of the function. So that is 3 minus x squared. So clearly we can use direct substitution here, and that will give us 3 minus 1 squared, 3 minus 1 squared, or 2. And now we need to find the right-handed limit. So the right-handed limit is going to be the limit as x approaches 1 from the right of our function f of x plus k. So now this comes the trickier part, right? What are we supposed to do here in order to make sure that this k will allow our function to be continuous, right? This is different from what we were looking at before, but if we think about it for a minute, I think we can come up with a pretty clever solution. So and feel free to pause the video and attempt this problem yourself if you haven't been doing so already. But now I'll assume that you've already given this a shot. So really, we need to do, what this comes down to really is we need to think about what it is that we're trying to find. We're trying to figure out for what value of this k here will allow our function f of x to be continuous at x equals 1. How can we say the function is continuous? Well, we can say the function is continuous when it meets these three criteria. So we've met the first criteria, and in order to meet the second criteria that the limit does exist, we need the left-handed limit and the right-handed limits to agree. We already have a value of 2 for the left-handed limit. So now what we have to figure out is for what value of k will this right-handed limit also equal to? And so clearly we would use direct substitution for this type of problem anyway. So then what we can do is we can set up this expression like this. It's 5x plus k equals 2. And so you can then go on to use direct substitution as we would for this type of limit. And that would just give us 5 times 1 plus k equals 2. So this is a very basic algebra problem here. Now we just have 5 plus k equals 2, and we need to solve for k. And this then is going to tell us that our k is simply going to be equal to 2 minus 5, or negative 3. So this is going to be our answer for this problem. Our k must equal negative 3 for our function f of x to be continuous at x equals 1. Alright, so that brings us to the end of this video. Hopefully, everything made some sense here, and this, you got some use out of the video. If you did, please show your support by liking and subscribing. Leave in the comments any questions you may have and what you would like to see for future videos, and I'll see you in the next one.